What we have here is a molecular equation describing the reaction of some sodium chloride dissolved in water plus some silver nitrate also dissolved in the water. They're going to react to form sodium nitrate, still dissolved in water, plus solid silver chloride. And if you were to look at each of these compounds in their crystalline or solid form before they're dissolved in water, they each look like this. But once you get dissolved in water, and that's what this aqueous form tells us, it tells us that each of these compounds are going to get dissolved in water. They're no longer going to be in that crystalline form. Instead, you're going to have the individual ions dissociating. So, for example, in the case of sodium chloride, the sodium is going to dissociate in the water. Sodium is a positive ion or a cation, and so it's going to be attracted to the partially negative oxygen end. Remember, water is a polar molecule. That's what makes it such a good solvent. Now, the chloride anions similarly are going to dissolve in water because they're going to be attracted to the partially positive hydrogen ends of the water molecules. And the same thing is going to be true of the silver nitrate. The silver ion, once it's dissociated, is going to be positive, and the nitrate is a negative. It is an anion. Now, in order to appreciate this, and write an equation that better conveys the dissociation of the ions, we could instead write the equation like this. This makes it a little bit clearer that, look, the sodium and the chloride aren't going to be necessarily together anymore. The sodium is going to dissolve in the water, like we have here. The chloride is going to dissolve in the water. The silver ions are going to dissolve in the water, and so are the nitrate ions. So this makes it a little bit clearer. And similarly, on this end, with the sodium nitrate stays dissolved. So we can write it like this with the individual ions dissociated. But the silver chloride is in solid form. You could think of it as precipitating out of the solution. This does not have a high solubility, so it's not going to get dissolved in the water. And so we still have it in solid form. Now you might say, well, which of these is better? Well, it just depends what you are trying to go for. This form up here, which we see more typically, this is just a standard molecular equation. Molecular equation. It's in balanced form. We always want to have our equations balanced. This right over here is known as a complete ionic equation. The complete's there because we put in all of the ions. And we're going to compare it to a net ionic equation in a second. Complete ionic equation, sometimes just known as an ionic equation. Now, why is it called that? Well, because we're showing the individual ions as they're dissociated in water. Now, what would a net ionic equation be? Well, let's think about that a little bit. Let me free up some space. So one thing that you notice on both sides of this complete ionic equation, you have the same ions that are dissociated in water. So for example, on the left-hand side, you have the sodium that's dissolved in water, and you also have on the right-hand side sodium dissolved in the water. It's not, if you think about the silver chloride being the thing that's being produced, this thing is in ionic form and dissolved form on both sides of this reaction. And so you could view it as a spectator, and that's actually what it's called. It's called a spectator ion. Spectator ion. If you want to think of it in human terms, it's kind of out there and watching the reaction happen. Its value in this reaction is, well, it was part of the sodium chloride, and it's provided, so the sodium chloride is providing the chloride that eventually forms the silver chloride, but the sodium is just kind of watching. Similarly, you have the nitrate. The nitrate is dissolved on the left, and the nitrate is dissolved on the right. So the nitrate is also a spectator ion. So if you want to go from a complete ionic equation to a net ionic equation, which really deals with the things that aren't spectators, well, you just get rid of the spectator ions. So you get rid of that, 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 and then you see what is left over. Well, what we have left over is we have some dissolved chloride, and we write aqueous to show that it is dissolved, plus some dissolved silver, plus some dissolved silver. Once again, to show that it's dissolved, we write aqueous. And if you put those two together, you are going to get some solid silver chloride. And what's useful about this form, it's more compact, and it's very clear what is actually reacting, what is being used to build. And you could say, hey, however you get your chloride into the solution, however you get your silver into the solution, these are the things that are going to react to form this solid. Instead of using sodium chloride, maybe you use potassium chloride, and the potassium in that case would be a spectator ion. But either way, your net ionic equation would be what we have here.